Alright, in this video we study series. So first consider a sequence of real numbers. A series is formally defined as this. It's a sum n equal to 0 to infinity, and we add this. That means we have a 0 plus a 1 plus a 2 plus and so on, and this addition continues indefinitely. However, we should note that, at this point, this sum doesn't mean anything because we don't know if this has any value or not. And also, we should note that this order of addition matters. Okay, it's first we have a 0, to which we add a 1, to which we add a 2, and so on. Okay, so we cannot just swap the orders of these numbers. So we cannot do something like this. We first we take a 100, and then we add a 51, and then we add a 33, and so on. We cannot do this. Okay, so order is important. Okay, here's an example of a series that is called a geometric series. That is a times r to the power of n. And a and r are some constants, real numbers. Okay, so this means a plus ar plus ar squared plus and so on. And here we assume that r to the power of 0 is 1. This is understandable if r is non-zero, but we also assume that 0 to the power of 0 is also 1. So this is called a geometric series. And this is a sum of a geometric progression. All right, now let's define the meaning of series more precisely. Suppose we have a series. At this point, this, as we have told before, this is just a formal expression without any meaning. But anyway, suppose we have this, and for a given non-negative integer n, let's define this sum, okay, from 0 to n, ak. So that is a0 plus a1 plus and so on up to a n. So this is a well-defined sum because this is a finite sum, and this is called nth partial sum of this series. Now, based on these partial sums, we can define a new sequence of real numbers. That is, S0 is A0, S1 is A0 plus A1, S2 is A0 plus A1 plus A2, and so on. And ASN is a0 plus a1 plus and so on up to an. So that is this sum, n a k. So in this way we can define a sequence of real numbers. And if we take the limit of this sequence, so that is this limit, Sn n going to infinity, then formally we can write like this, k from 0 to n, a k. So if this converges, then we write as this, k from 0 to infinity, a k. So if this converges, then this is the series, this series, okay? So here we use n for the index, and here we use k for the index, but it doesn't matter, it's just an index. So it's a bounded variable, so to speak. So if this converges, then this is the value of the series. And we say this series has a sum, or the series converges. And if the value of this limit is say alpha, then we write this series. Okay, in this case we write n here. N equals to alpha. Okay, let's consider again the geometric series. Okay, this and from 0 to infinity a r to the power of n. And to evaluate the value of this series, whether it converges or not, we first consider the partial sum. So okay, from 0 to n a r to the power of k. And as you may know, this is equal to a 1 minus r to the power of n plus 1 minus r when r is not equal to 1. Okay, and otherwise this is, if r is equal to 1, then this is, actually it's not a geometric sequence here we have, but it's a arithmetic series, so it's a times n plus 1 when r is equal to 1. Then we can see this partial sum converges as n goes to infinity if and only if this r is less, the absolute value of r is less than 1. Okay, so if this is the case, then Sn converges to a over 1 minus r. So that means in this case, and this case alone, this series has a sum, which is this value. Now let's see a basic property of series. So here's a theorem. Suppose we have two series, sum of an's and the sum of bn's. So if this series and this series have sums, so that means if they converge, then for any real numbers k and l, we have the sum of the linear combination of an and bn is the linear combination of the sums. Very simple, and it makes sense. So it may appear that this is intuitively trivial. However, when something involves infinity like this, very strange things can happen. So we have to prove this is indeed true. So how do we do that? So let's prove this. First, let's define the partial sums. Let's say Sn is equal to the partial sum of a's, ak, and Tn is the partial sum of b's. This is n and bk. And by assumption, we're assuming these converge to some finite real numbers, right? So by assumption, there exists some real numbers, let's say S and T, such that the limits are these numbers. So the limit of Sn is equal to S, and the limit of Tn is equal to T. Okay, then next, let's define another partial sum, or maybe we should say a finite sum. Anyway, so un is equal to the partial linear combination of oh, wait a minute. So if we use the index k, then it's a bit confusing. So let's use m and l, b, m up to n, where k and l, which are real numbers, are arbitrary. Okay, but since this is a finite sum, we can write this sum as this. So finite sum, this is okay. It's just a distributive law. And m, b, m. So which is k times s, k times sn plus l times tn. Now for finite sum, from this line to this line is trivial. It's just adding and multiplying just ordinary numbers. In the case of series, if this n is infinity, then it's not trivial. That's what we are proving right now, actually. But anyway, so this is okay, and so this is okay, and we know that limiting operation is a linear operation. So this converges to k times s plus l times t as n goes to infinity, and we are done. Now suppose this series converges, okay, and consider this partial sum, okay, from 0 to n a k. Then if this converges, that means this sequence converges, right? So this Sn converges to, let's say, some value S. And then that means this sequence is by the property of real numbers, is a Cauchy sequence. It's Cauchy. It's a Cauchy sequence. So if you don't remember what a Cauchy sequence is, it means this. So roughly speaking, if k and l are large enough, sufficiently large, then if k and l are sufficiently large, then the difference between sk and sl is arbitrarily small. So this is what a Cauchy sequence means. Well, more formally, we can formulate in the following manner. For any epsilon that is positive, there exists some natural number such that for all k and l, which are natural numbers, the following holds. If k and l, let's say k is greater, okay, if k and l are greater than or equal to this n, then the difference between sk and sl is less than epsilon. So for any, so epsilon can be very small as long as it is positive. Okay, for any small epsilon, if we take large enough k and l, then the difference between sk and sl is less than epsilon. So this is the definition of a Cauchy sequence. Okay, and as we have learned in calculus, basic calculus, a sequence converges if and only if it is a Cauchy sequence. Okay, now if we apply this this part to the partial sum, like this one, okay, Sk is A0, A1, A2, and so on, and we're assuming K is greater than L, okay, so AL appeared somewhere, and AL plus 1, and finally we have AK. And SL is this, and it stops at AL. So if we take the difference, then SK minus SL is this part. Okay, AL plus 2, and so on, and AK. So let's say if we have, if this K and L can be anything as long as K is greater than L and L is greater than or equal to some natural number n. Okay, so if we set K equal to L plus 1, then Sk minus Sl is just AL plus 1. This is the only term left. And if the absolute value of this is less than any positive real number epsilon, then what this means is that this sequence AK, this one converges to AK converges to 0. So that's the implication. So our starting assumption here is that this series has a sum or converges. Okay, so starting from this, we conclude that the sequence AK converges to 0. So here's a theorem. So theorem: if the series AN has a sum, then the sequence AN converges to 0. Okay, now be careful with the direction of this implication. It says if the series converges, then the sequence converges to 0, but not vice versa. Okay, so that means even if a sequence converges to 0, the series, the corresponding series, may not have a sum. Let's see this example. AN is equal to 1 over n, where n is from 1, 2, and so on. Okay, clearly this sequence converges to 0. So limit n going to infinity, an, this converges to 0. That's clear. However, this series, if we sum, not from 0, but from 1 actually, this does not have a sum. Let's see this. So if we take this summation, this is 1 plus 1 over 2 plus 1 over 3 plus and so on. And now we express these as each term as a integral. So from 1 to 2, integral of 1, it's a constant function. So since this is just a constant, if we integrate it, it's just between 1 and 2, so it's just 1. And 2 and 3, 1 over 2. And 3 from 3 to 4, 1 over 3 dx, and so on. Okay, so far so good. These are just constant functions. And this is greater than or equal to this. From 1 to 2, 1 over x. Okay? And from 2 to 3, 1 over x. and from 3 to 4, 1 over x dx, and so on. Okay, so this is the case because if you plot the graph of this function, let's say from 1 to 2, the function basically looks like this. It's a monotone decreasing function. So when x is 1, then the value of 1 over x is 1. And when x is 2, the value of the function is 1 over 2. Okay, so in this interval, this function value is always less than or equal to 1. Okay, so 1 over x is less than or equal to 1. Therefore, this integral is greater than or equal to this integral. And the same applies to this part. So between 2 and 3, let's say, we have, this is 1 over 3. So in this interval, the value of this function, 1 over x, is less than or equal to 1 over 2. So this, and this, and so on. So in total, we have this inequality. But now we have the same function in all the integrals here, and so on. And we can just concatenate these intervals to have the integral of 1 over x dx from 1 to infinity. So this is an improper integral, but this is easy to integrate. The result is just a natural logarithm of x from 1 to infinity, which is infinity. So this sum is greater than or equal to infinity, so to speak. That means this sum does not converge to a finite value. Therefore, even though this sequence converges to 0, the series, the sum, does not converge. So the converse of this theorem does not hold. Okay, next we study a special class of series, that is positive term series. Positive term series. As the name suggests, it's a series such as this one, an, where each term is positive or 0 for n equals to 0, 1, 2, and so on. The reason why we consider this special series is that they have a nice property that the sum does not depend on the order of addition. In general, if the term contains both positive and negative terms, then the result of this sum may depend on how we add, in which order we add these terms. But in the case of positive term series, it doesn't matter. In whichever order you add them, we still get the same result as long as it converges. Now, if we consider the partial sum of a positive term series, let's see, k from 0 to n, a k, then since each ak is non-negative, this is a monotone increasing, or maybe more precisely monotone non-decreasing sequence. So this partial sum is a monotone non-decreasing sequence, right? So if this sequence is bounded above, then according to the monotone convergence theorem, this will converge to some finite value. If you don't remember monotone convergence theorem, please review it. Monotone convergence theorem. Let's see an example. Consider this series from 1 to infinity and 1 over n to the power of alpha, where, so this has a sum if this alpha is greater than 1. And let's show this. First of all, we consider the partial sum, and from 1 to capital N, 1 over n to the power of alpha. So this is, if we just write down all the terms, it looks like 1 plus 1 over 2 to the power of alpha, and 1 over 3 to the power of alpha, and so on, and 1 over n alpha. And now this is just like a previous example, we express this in terms of an integral. Okay, from 1 to 2, we integrate this. From 2 to 3, we integrate this, and so on. And from n minus 1 to n, we integrate this. Now, this is less than or equal to this. So from 1 to 2, integrate 1 over x to the power of alpha. Let's write dx on the numerator here to save space. And this is integral from 2 to 3 dx over x to the power of alpha, and so on. Minus 1 and x to the power of alpha. This is because if you draw the graph of this function, it looks like this. So this is 1 over x alpha. And let's see. For example, if we take the interval between 1 and 2, and 1 over 2 to the power of alpha is this. Okay, this is 1 over 2 to the power of alpha. And this graph is always above this value, right? So therefore, this integral is greater than or equal to this integral. And the same applies to all other terms. And now we combine all these integrals together. So it's an integral from 1 to n dx and x to the power of alpha. And of course, this is less than or equal to 1 plus. So we take this n to infinity. Okay, then this is an improper integral. And if we integrate this, we have 1. And so this is x alpha plus 1. Wait a minute. So this is alpha. So if we integrate this, okay. So this is negative alpha plus 1. So it's 1 over negative alpha plus 1. And from 1 to infinity. And this, so if we put infinity here, that's 0. And if we put 1, that's negative. So that's, let's see, 0 minus 1 over this. So that is 1 plus, wait, what is it? 1 over alpha minus 1. So that is alpha over alpha minus 1. Note that we're assuming that alpha is greater than 1. So this is greater than 1. So after all, this series is bounded above by this value. So according to the monotone convergence theorem, this series converges to some value. We now prove the following important theorem that says any positive term series can be summed in any order and we still get the same result as long as the series converges. So here it is. Suppose the series, this one, n from 0 to infinity, we add an, has a sum. That means this converges. And let an of k be a permuted sequence of an. So what this means is this. We have a sequence A1, A2, A3, and so on. So we shuffle, so we permute the order of this sequence. So for example, we get A303, A52, A22, and so on. So this 303 can be n of 0, and this 52 can be n of 1, and this 22 is n of 2. So, well, we can shuffle in any order, but just this be any permuted sequence, arbitrary permuted sequence of an. Okay. Then we have this equality. K from 0 to infinity, an of k is equal to n from 0 to infinity, an. So that means the sum, this series here, this permuted series, has the same value as the original series. Now let's prove this theorem. Okay. And to prove this, let's say we have alpha. So we are assuming that the original series has a sum. So let alpha be that sum. Okay, and consider the first I terms in this series, this permuted series, an of k. So that is an of 0, an of 1, and so on up to an of I. Okay, so, and let capital N be the maximum index of these from n0, n of 0, n of 1, up to n of I. Okay. So, for example, if we take, let's take the first 3 terms, okay, for example, and in the previous example, oh, I erased it. Anyway, so let's say we have this original sequence, and if we permute the indices, then we may have A303, A52, A22. Okay, so just take the first 3 terms in the permuted sequence. Then this maximum of these indices is the maximum of these indices. Okay, in this case it will be 303. So in this case n would be 303. Okay, now consider the sum. Okay, so an of 0 plus an of 1 plus up to an of I. So this is greater than or equal to a1 in this is original sequence, a2 up to an. So in this example, if we add these 3 terms, A303 plus A52 plus A22, that is greater than or equal to A1, A2, A3, and so on up to A303. Right? Because since we are keeping this largest index here, all the terms in the left-hand side here, so including 303, 52, 22, they are all in the left-hand side, on the right-hand side. Therefore, and on the right-hand side, there are extra terms. There may be extra terms. So therefore, and also, we are only considering positive term series. So all of them are positive. Therefore, the right-hand side can be only greater than or equal to the left-hand side. So therefore, this inequality holds in general. But this left-hand side here, this one is less than or equal to alpha, which is the limit. Okay, the limit here, this one, the sum of this series. Therefore, the left-hand side is bounded above by alpha. And of course, this is a positive term series, so it is a monotone. This permuted series is a monotone increasing series bounded above by alpha. Therefore, it will converge. So let beta be the sum of this permuted sequence series. So an of k. Then we have beta less than or equal to alpha. Now let's introduce an important notion of dominating series. Here's the definition. Dominating series. So let sum of ANs be a positive term series. And we say, so this is one series, and suppose there's another series of Bn. Okay, and converging sequence, a converging series. So the limit is, let's say the limit is beta. Then we say this series, the second series here, is a dominating series of this first series if the following holds. A dominating series of AN. So here's the definition. That is, for every term and 0, so that means natural number including 0. For all n, we have an less than or equal to bn. Okay, so that means every term an is bounded above by the corresponding term in this series bn. That is, so here's the theorem. If this series an has a dominating series, then it has a sum. Okay, so even if this is difficult to calculate explicitly, if we can find another series that converges and dominating this series, then we can be sure that this has a sum. And we will see some of such examples in a future video. And that's all for this video today. See you later.